Sounds like a sweet deal. I'd choose San Francisco, I think. All right, so welcome to the third lecture in 4820. We're sort of at the peak now this week in introducing you guys to Lisp as our programming language. Starting next week, we'll consolidate that and then head towards our first block of topics in machine learning, vector space models. Just like last week, I actually didn't prepare a lot of previously on Twin Peaks for today because I felt we are initially going relatively slowly, and I would like to think it's not really the best use of our time to now use another 10 minutes to go over the Lisp Essentials. This is essentially a high-level summary. Symbolic expressions is what we manipulate. We break them into atoms or, so far, lists of as expressions. So lists are the one data structure we have so far. We refreshed our understanding of recursion, looked at the special case of tail recursion for improved efficiency, talked about the semantics of Lisp in terms of evaluation and quote, the special form quote, as a means to suppress evaluation, so to essentially navigate the code data chasm, the divide, where as expressions can serve as both code or data. Looked a little bit at how lists are represented internally and how what built-in functionality there is to operate on lists, and concluded with a review of the distinction of various notions of equivalence, token identity versus structural equivalence. And today we'll put in a lot more basic core common Lisp, spend some time on higher order functions, learn some aspects of I was going to say syntax, but that's not right because you know everything about the syntax. And the flexibility we have in defining our own functions and specifying their argument lists. Spend a little bit of time talking about iteration as an alternative to recursion and the mighty Swiss Army knife of iteration built into Common Lisp called loop, and introduce a collection of additional data structures. I hope to get through all of that. Before we do that, have you checked the course page this morning? Wake up, coffee, course page, remember? Actually, this notice wasn't there when you woke up, fortunately. So someone who shall rename unnamed a little, like half an hour ago, broke our development environment. And I thought I had fixed it, but it turns out it worked upstairs for me on my machine, but it doesn't seem to work down here. So there may or may not be live coding in this lecture, as I wanted to do. And currently you can't do any coding on the EFI environment, but we certainly hope to have this fixed again pretty soon. Check that page regularly, please. So this is essentially where we wrapped up a little hastily last week. And this is actually one of the fundamental distinctions, one of the few actual distinctions between Scheme as one dialect of Lisp and Common Lisp as another dialect of Lisp. We often break those dialects into the Lisp 1s and the Lisp 2s, and Common Lisp is a Lisp 2, in the sense that a symbol, a name, an identifier, can at the same time have both a value definition, can function as a variable, and a function definition. It can function as a function. And that means we need some mechanism to distinguish between these two usages, and the function special form, abbreviated hash quote, or sharp quote, gives us the function object associated with the symbol. I type in a symbol, it evaluates to its value. I type in hash quote a symbol, what comes back is the function associated bound to that symbol. So let's look at how that works. I define a function called foo. I define a variable called foo. So I exploit that possibility of having both bindings for the same symbol. This is the same symbol foo. So now it has both a function and a value binding. And here I use both. And here the syntax actually disambiguates. The first element in a list is a function call. The first element is an operator. So Lisp will, of course, look for the function definition associated with that symbol. Everything else arguments, and they will be evaluated. And so this is the value binding. That's the variable foo. And I compute 42 times 1,000. And I can evaluate foo, and it evaluates to its value. And I can ask for the function. So this is how Lisp prints a function object. That's implementation dependent. That's just some way of announcing to us this is a function object. That's something I can invoke. And now how do I invoke it when I actually have a function object as obtained by hashcode foo here? I need a function. I think I see no reason why funcall. Yeah, I think funcall actually is a function. So I need a mechanism to say, take this function. So hashcode foo is a function object. Call it, and then I can give it any number of arguments. So this funcall here has the exact same effect as what happens because of where I use the symbol foo in this expression up here. And this is of course the normal way of function invocation, but we will very soon see that it can be convenient to talk about the function objects explicitly and have a mechanism to invoke them under program control. So the pair of hashcode and funcall, and there's also a variant of funcall called apply, are useful when I pass around functions as arguments and at some point want to invoke them. So that's the fine points of common Lisp as a Lisp 2, the duality of value and function binding that a symbol can have. Scheme is a Lisp 1. A symbol is either the name of a function or of a value. It can't have both at the same time. That has the benefit that it doesn't require funcall. So why is this relevant to us? Because we will encourage you to take advantage of one aspect that all Lisp dialects share and emphasize, the notion of higher order functions. And we'll call a function that accepts functions, or a function object. I'll often use both terms interchangeably. So functions that take functions as arguments are higher order. Likewise, functions that return functions are what we call higher order. So they are essentially functions that operate on functions. Either take them as input or return them as output or both. That's the definition of a higher order function. And from that it follows, well, to make that feasible, functions have to be first-class objects. They are equal citizens, just like all of the other data types. I can create them dynamically at runtime. That is, code can create functions, can pass them around as arguments. I can return them. I can store them in variables. I can store them wherever I can store data. They're just like any other type of data. That's what it means to be a first-class citizen. For example, a classic in functional programming, a function that takes a sequence and a predicate, a test, and returns a sequence that only contains those elements from the original sequence that satisfy the predicate. So let's look at an invocation. I give myself a variable that contains a sequence of numbers, and then I filter that sequence using the predicate even p. So that means I expect that the result will only contain those numbers that are even from the original sequence. How does that work? Let's look at the code a little. So here we have highlighted the one parameter that is a function object the test. I can give it an arbitrary predicate and it will filter according to that predicate. And we use the cont, the case statement with 3 clauses. The first one says, that's the base case, given an empty list, nothing remains to be filtered, return an empty list. So null is the predicate that tests for empty list. In that case, I'm done. I return the empty list. Second case is, let's look at the current first element. So this is a recursive function. It will process one element at a time. And because the test is specified as an argument, I need to use funCall to invoke it on the first argument. So the next clause in the cont says, is the first element of the list something that satisfies test? Invoke test on that first element. Interpret what comes back as a truth value, because we're here in the predicate slot of a cont clause. If that tests true, then do the following. Then return, a const containing that first element and a recursive call over the remaining list, and still using the same test. So what happens here is I test the first element against the predicate. When that succeeds, that element better be part of the result. Because I'm recursively going through the list, I need to, at this point, say, you, first element, are part of the result. Hence, I cons you on applying the same filter function on the rest of the list. When the predicate is not satisfied, so the default case here, the test in the third cont clause is t. The symbol that evaluates to itself is interpreted as true. Then the current first element does not satisfy the test, must not be part of the result, hence I just recurse over the rest and effectively discard the first element. That's an idiom almost in recursive, working through a list one element at a time recursively in functional style. I assume many of you have seen this pattern, if not this function, and recognize the idiom. So this is how it works. And what we have is a function, of course. We define a function here. It's recursive. It calls itself. There are conditionals. There's a branch in the computation depending on various conditions, the cont clauses here. These are predicates. Null of list or funCall test. Test is a predicate. And we use lists, the same basic data type, for both the code, the function definition, for example, and the function call, and the data, the sequence of numbers that we process. So this, in a sense, instantiates all of the fundamentals that we introduced last week already. Any questions on this? This is important. This should be crystal clear. Okay, I'm happy that it appears to be clear at least. Hopefully crystal clear. Certainly before too long. So a twist on functions as arguments or return values is that I can have anonymous functions, and that's just a function object that doesn't have a name. That's not the function binding function value of a symbol. I create these using lambda. So here Lisp betrays its mathematical origins, the lambda calculus. The syntax is actually very similar to defun. It's a list where the first element is the symbol lambda that says anonymous function. Then there's a parameters list and a body. So it's a function definition without the defun and the function name part replaced by a lambda. And for example, I can create an anonymous function object here that takes one parameter and tests whether that parameter is both greater than 20 and less than 50. So I use AND, the Boolean connective, and greater than and less than built-in predicates on numbers and combine them into a conjunction. give that as the test argument to foo, and it returns to me the sequence, or the subsequence, the selection of elements from the original value of foo that satisfy this test. And anonymous functions are typically used for functions that I don't need to name, that are very local to one piece of code, ad hoc functions, and also that are sort of short enough to fit onto a few lines. When I write a very complex function, it may be advisable, even when I only use it locally, to actually define it, give it a name, so that I can test it in isolation. And so that's just an additional mechanism I have. And I think I said in the first lecture, Lisp has its appeal, because more and more programming languages become more and more like Lisp, and Lambda probably reminds you of something. You're beginning to see that more and more in languages, including Java 8. Lisp is where it was from the beginning. So that's the Lisp legacy spreading itself here. No magic here, I would like to think. Here I use an anonymous function as an argument to a higher order function filter, but I can equally use it to construct an anonymous function that will be the return value of a function, the other interpretation of higher order function. So, somewhat constructed example, you might say. I have an application where I frequently need to test numbers for being in a specific range, and the boundaries of the range are, they change dynamically. And hence I give myself a constructor, a function that constructs another function, takes two parameters, the lower and upper bounds of the range, and constructs a function object, an anonymous function object, that tests the conjunction of greater than and less than, so parallel to what we had before. And now I can replace what I had earlier with a call of make range test that will return a function object. That's what the body of this function does. And that function object can be the second argument now to another function. So make range test is a higher order function, not because it takes a function object as its argument, but because it returns one. So we've now seen an example each of the two ways in which functions can be higher order functions, operate on functions. Okay, that's actually a powerful technique that Lisp exploits at length in its standard library, and that will often be convenient to us in writing our own programs, because passing in functions is a good and flexible way of parameterizing other functions, of adapting their behavior. And we see that in the filter function. Filter is a generic mechanism to go through a list and take out those elements that satisfy a certain test. And we parameterize, we customize what the function actually does by giving it a test function object that determines the selection criteria. So that's the mechanism of combining functions, of composing functions, and of creating flexibility by essentially dynamic configuration using function objects as arguments or return values. All right. No questions? Comments? You're already thinking about summer school, San Francisco 2017. I actually used to live in San Francisco and teach at a university in the area. And when I moved to Norway, sort of one of my early experiences was that it's sometimes hard to get the people in the audience to react. So there's this, you'll soon experience that, Mohaf. That's why I'm bringing it up. Some days there's just this wall of faces and they look at you, and some not. That's great. And some bring out their cell phones. And currently we don't have a policy on that. And it's really sometimes an important challenge, I feel, to somehow break through that wall. And, I'll every now and again, every week, I think I'll make at least several attempts. And today I feel the wall is somewhat stronger than it used to be. And then sometimes telling a story can actually help reduce the wall, or there are many techniques we can apply. But one important technique is also to learn to tolerate uncomfortable silences. Because we ask a question, and on those wall days, nobody might answer it, and then we just don't know whether the question is trivial and you feel insulted that we ask you to say 42, obviously, or whether you've long sort of shut down and think about San Francisco 2017 and we have lost you for the lecture, or at least for part of the lecture. And so one function of those questions is actually for us to calibrate how we lecture and at what speed we go through the material, and what to say twice or 3 times, and what to just do very quickly. So it's actually good for you to sort of let down the wall and interact with us, I believe, because then you get a lecture that is more customized to what you actually need as a group. And so uncomfortable silences arise when the question is in the room and nobody feels like answering it. And in the teacher training classes that I took, we actually were trained to tolerate uncomfortable silences. And Norwegians have a fairly low threshold for uncomfortable silences. They're not Finns. So it's important to sometimes just sit it out and stare you out. I'll try that too. All right, so much for the back to Lisp. No questions on higher order functions. Let's move on. Different topic. It's again, like last week, a potpourri, a collection of topics that you'll find useful in doing the actual programming assignments. Now, parameter lists. So far we've seen a list that contains some number of symbols. That means there's a fixed number of arguments to the functions we define, and they are specified by order. The first parameter corresponds to the first argument I give the function when I call it, and so on. But there are other mechanisms. For example, I can make parameters optional, and there is some special syntax. So I insert symbols that look funny, but they're just symbols. So ampersand is a convention that the Lisp designers chose for that symbol that I can put into the parameter list to say parameters following ampersand optional are optional. That means I can not provide an argument when I call the function, and that will still be a valid use of the function. That is a mechanism to define what we call polyadic functions, functions that take variable numbers of yeah, I think that's the right term. Variable numbers of parameters, variable arity functions. I'll often want to provide a default value when the parameter is not specified. What should its value be? Because the body of the function will most likely use that parameter, and so it needs to have a value. Here, a pair, function name and default value. That means Z will have 42 as its value when not specified. Now you might guess, you should guess, but Y doesn't have a default value, it's optional. So I call foo with just 1 as one argument. That 1 becomes the value of X. That's not optional, that's the first parameter. So what's going to be the value of Y? Well, we worked that out programmatically here. It appears to be nil, because what the function does, it just returns the values of X, Y, and Z, so I can look at them. And when I just give it 1, Y and Z or z are not specified, then what comes back is nil as the value for y and 42 for z. So optional parameters that don't have a default value declared in the function definition default to nil. The Lisp default is almost always nil. So when you ask, okay, what should this be? And it's not determined explicitly, then it's most commonly going to be nil. Empty list or false. That's conveniently overloaded. I can give it 3 arguments, and then they all have those values and come back in that order. So that's optional parameters. I can take that one step further and liberate myself from the order coding of parameter to argument correspondences. So I can define functions that identify their parameters by a given name, and then in calling the function I can specify them in any order because I actually tell the function which one is which. So that's the ampersand key parameter. Anywhere inside of the parameter list can be combined with ampersand optional. And here I say I again have one obligatory parameter, one mandatory parameter x. I have 2 key parameters y and z. Do the same thing, just return them so I can inspect them. And nothing has changed here, so key parameters are optional. They have that in common with optional parameters. But when I actually want to give specific values, I need to name them. And I name them by the so-called keywords, which is the parameter name preceded by a colon. That's another symbol convention. So colon z is a symbol, and it's actually a symbol. The symbols that start with a colon are self-evaluating. I don't need to quote them. That's convenient. Just a second. So here I say I give it 3 parameters. The first one is order coded or positional. And then I give it a value for z, and I give it a value for y, but I can actually give these 2 in any order. So in this case, in this example, in the reverse order to the function definition. Keyword parameters are bound, are identified by their name, not by their position. Question over there. Yes. So keyword parameters are identified by name, and hence everything you define as a keyword parameter, when you call the function, you actually need to provide the names as keywords. Colon and function name as a symbol. Yes? Could I also not provide the names when they're keyword parameters? No. Then I should make them optional, and then again they are positional. So there's a fundamental choice. Either they're identified by position, order, or by name. And the positional ones can be mandatory or optional, and the keyword parameters are always optional. So I can't have a mandatory keyword parameter actually. I now realize. But I can have more flexibility here. This is not all. I can also have, this is effectively another way of defining functions with a variable number of parameters, the so-called ampersand rest parameters. Essentially will collect everything from that point in a list. So here I say I want to define a function average that takes any number of numbers as arguments for any equals 1 or greater. So the function is not well defined with no arguments. Average requires at least 1 parameter. And I sort of encode that by saying it needs an x. That's 1 obligatory parameter. And from there on, any number, it can be 0 from there on, and collect them in a list of rest parameters for me, and that list will be called rest. So again, ampersand rest is a symbol that has special meaning inside of the parameter list and only there. And rest, this one here, is just the name of a parameter. So what I've coded red is sort of parameter list syntax, and what is black are parameter names and default values. And now I say, okay, construct a larger list of all of the numbers, including x, by just putting x to the front of rest. So cons x rest is all of the parameters, including the first, because the rest only starts after x. The first parameter will be bound to x. And then I can add them together. And to do that, I want to invoke the function object that is bound to the symbol plus. So hash quote plus is the addition function. It's the function that's invoked when I call plus, the operator plus. So I get that function object and I use apply. And I use apply because here I have a list of arguments. So that's the distinction between funcall and apply. So apply hash quote plus to all of these numbers will be the sum of all of the numbers, and I divide that over the count, the length of the list containing all numbers. That will be the average. I can call that with a single number, and the average is that number. It's divided by 1. And I can call it with any number of arguments, and then the average will follow the recipe there. So that's yet another mechanism to define functions that take variable numbers of arities. And we've actually seen many such functions. Can you give some examples? Uncomfortable silence. Sorry? List. List takes any number of things and returns all of them in that order as a list. What would happen if list is called with no arguments? It returns all of those arguments as an empty list. One more example. A function that takes a variable number of arguments. We've seen several. Plus. Plus can take 2 or 3 or 5 numbers. It can also take 1 number, and then it returns that number. Any suspicion what would be a sensible, is there a sensible thing that plus could return without an argument? Nil. I said not long ago that that Lisp will often use nil as the default value, but plus is a numeric function. So it's only applicable to numbers, and it returns a number. So plus returning nil would break its contract. It's very convenient that the numeric functions always return numbers, and nil is overloaded. It can be a truth value, it can be interpreted as false, it denotes the empty list, but it has no interpretation as a number. That would be overloading way beyond sanity. Any other idea? That was a plausible idea, but what? It should return 0 because that's the neutral element of addition. So when I don't add up anything, what I have is 0. Thank you. All right, so yeah.
Does that mean that apply needs a function that can take a variable number of arguments every time?
No. No. So it does not. Sorry, just to repeat the question so we get it. So. Does apply require a function that takes a variable number of arguments? No. The distinction between funcall and apply is that I give funcall, so I have funcall function object, arguments. 1, 2, 3, however many arguments. And those arguments will be mapped to the parameters of the function object, just as if I called the function. The difference with apply is I do apply a function object list of things. And the elements of that list will be mapped to the parameters of the function object. So if I give apply function object a list of 3 things, then I need a function object that accepts at least 3, that accepts 3 things. If I were to use funcall with that same function object, I would say funcall function object and then 3 more things. So funcall is a function of variable arity, and it will expect as many arguments as the function object expects, plus the function object itself. Apply is not a function of variable arity in the same sense, because it expects a function object and a list containing the right number or a compatible number of things, objects, entities that the function can take as arguments. So that's the distinction. And because here I actually have, so rest, there's kind of an idiomatic correspondence here. When I have rest parameters, then I will typically use apply to invoke a function on those. Because the arguments I want the function to take already are collected in a list. Yes? So could I make the x in the average definition optional? I would then have to, well, could I make it optional? So why do I do it this way? Was the question I thought you might ask. That's just hardwiring the assumption that there's no point in computing the average of nothing. Because unlike for addition, 0 would not be a plausible average for nothing. And now you're asking more in terms of the mechanics of parameter lists. Could I say an optional parameter followed by rest parameters? That must be possible. And I think what that means is that when there are no arguments, that's fine. Then the optional parameter will default to its default value, and the rest parameter will be the empty list. When there are arguments, 1 or more, then the first one will be bound to the optional, the x, and everything that remains will be in the rest list. So yes, that is possible, and it is well defined. In the first place you said, here? So what would happen if I swap the x and the ampersand optional in the definition of foo? Then I would make all 3 optional. So I would no longer have an obligatory parameter, but I would have 3 optional positional parameters. Means I can call foo with 0 arguments, 1, 2, or 3. All right. Even though we're not missionaries, you might recognize some of these mechanisms from other programming languages. You know? Python has incrementally, I think, acquired more and more of the same notions. Named parameters, optional parameters. I'm not sure, does Python have rest parameters? It should. But that's another sort of, yeah, just flexibility, sort of thought through space of variance in defining functions that Lisp introduced very early and that has since been inherited by other programming languages. All right, that was a matter of convenience. There's no real depth here. That's just learning conventions of the language and how these symbols that start in ampersand are interpreted when they occur inside of a parameter list. Yeah, let's go through this and then actually take a break, which means I can try to fix our development environment for the live programming that I was going to do after this slide. So this is a slide I had last week already, and it's an important distinction. Equality, different notions of equality, and they break down into 2. Identity, being the same object. You can think of that as comparing pointers. am I looking at the same address location somewhere in memory, versus structural equivalence, being comparable for objects that have structure to have isomorphic structure and to have the same comparable values in all positions, for example. And so EQ slash EQL test identity, equal slash equal P test equivalence. And there's the duality EQ versus EQL, because EQ, which is really the cheapest possible test that can be performed, is defined for everything except numbers and characters. So the standard is not tying the compiler's hands about how to represent numbers and characters. EQL is like equal, it tests identity, but is also well defined for numbers and characters, that is to say numbers of the same type. Equal, so very often we use EQL and equal, and when we know we're really only comparing symbols or structures that we want to compare for identity, then we use EQ. So two lists that look very much the same are two instances of equivalent lists, hence they are not EQ, but they are equal. So that's the fundamental distinction between identity and equivalence. This doesn't have a well-defined answer according to the ANSI standard, but with EQL it does. So when I compare numbers, when I compare numbers, I might actually just use the equal sign, the numeric equality predicate. But when I compare things that could include numbers, then I should use EQL. And the default test will typically be EQL for built-in functions. Equal P has this sort of additional complication that it tries to accommodate some range of differences in otherwise equivalent structures or objects that can be meaningfully related to each other. For example, numbers of different types, but equivalent numeric value, an integer and a floating point number, or strings that differ in terms of capitalization. Personally, I'm not sure I've ever used equal P. I would maybe rather write my own equivalence predicate than sort of look up the corner cases that equal P caters for. And finally, all of these are the sort of generic equality predicates. That is, I can in principle use them when there is uncertainty or variation in the types of objects I want to compare. Often, of course, I'll know that these two things will always be numbers or strings, and then I might be better off actually using a type specialized predicate. The numeric equal sign is a comparison for numeric equivalence, or string equal is like string comp compares strings. These will give errors when given objects that don't match the type that they expect. Yes? Didn't we actually ask that question last week and answer it? And I wasn't quite sure of the answer. I said, try it out. I'm still not quite sure of the answer. I would actually expect false comparing. It's true you tested it. Okay, so the standard says that the numeric equal comparison is robust in number type. It will test as equal two numbers of different type, an integer and a float, or a rational number for that matter. Lisp has a built-in type for rational numbers. Okay, at that point, let's take a break here, and I'll see whether I can actually enable live programming for the second half. All right. There will be live programming, I believe. We can try to find out whether we should be doing more of that in future lectures or whether we rather leave that to the group sessions. From an earlier exam in an earlier version of this class, right? A function swap based on recursion. The function should take 3 parameters, x, y, and list, where the goal is to replace every element matching x with y in the list. Here's an example of the expected behavior. Swap all occurrences of the string foo with the string bar in the list as we see here. And I'll need your help in implementing that. I know you know how to do this. So here's our development environment. I thought before we do that, maybe we could play a little bit with identity versus equivalence. So I've defined control meta x to evaluate individual S expressions. You see it down here in the mini buffer as I evaluate it. For example, what do you think should be the result of, is the first element of bar equal to the third? Any opinions? I need your help. We're jointly coding here. We're working as a large team of developers. Yes, just barge in. Nth takes the nth element at index I. Think we had it on the slide last week, and the index is 0 based, so that should be the third element. Yes? I certainly thank you. So this would actually be an error because bar without stars, that's the pair programming spirit. You save. Sorry? It is indeed nil. And why is that? I mean, if we look at bar, there's foo and there's foo. It's nil because they're not the same foo, of course. But if we modify that and say, is the third element actually equal to the value of star foo star, then I had expected that to be true. It's possible that my showing off evaluation broke that. Yes, indeed. Ha! So we learned something here. Well, why is this true? No, I'll just stay here sitting. Because what I did here is I constructed a list of strings, and one of the strings was the value of the symbol star foo star. So list evaluates all of its arguments, the strings evaluate to themselves, the symbol evaluates to its value, and the value is this string. So here I actually end up with that exact same object. So the string foo in the third position is identical to that string foo that is bound to the symbol star foo star. The string in first position, however, is not. I make these equal, they all come back true, of course, because equal will consider 2 different instances of the string containing the characters F, O, O equivalent. Okay, so that was identity versus equivalence. Now let's write that function. Do you remember what it's supposed to do? Locked by another user on another machine. Steal it. Swap. How many parameters? X, Y, list, I think they said. Okay, any suggestions? Yes. Or here's a man after my own heart. Recursion, excellent. So we'll probably need a conditional evaluation. And what's the base case? I think they want us to swap. So when there is foo here in the second position, it should become, so yeah, replace x with y. It's really query replace what we're implementing. So you were suggesting the base case is? Yes, I was trying to ask a leading question. What's the base case? So you said let's work through the list sequentially using recursion towards the empty list. So the base case is so that the list is nil. And then we return nil. You're welcome to help improve our joint program here. If you observe anything that you think calls for improvement. So that's the first condition here. Test value. Now if the first element is, what did you say? Equal. I think you said equal. Then so when the first element, the current first element is actually equal to x, and we're dealing with strings, at least in what we said we should be doing, so you chose equal. Yeah, we didn't say case sensitive, so equal is probably the right choice here. And when that is the case, then we put x in that position and recurse swapping over the rest of the list. Otherwise, like this. Okay, evaluate it. Oops, an error. Nil is not of the expected type number. It says. And we see that we're here. So we're comparing equal sign list to nil. That is good actually, because that gives us an opportunity to reflect on what has just happened. Probably many of you have experienced this condition. An error has occurred and Lisp enters the debugger, which means I can now actually inspect the current state of affairs when the error occurred. Most importantly, I can look at the backtrace, and it gives me restart options here. And I find Slime not maximally helpful here, because the restart option it offers sort of at the bottom, where I used to look for the most plausible option, is kill this Lisp process. So I did this several times, not realizing that restart number 1 abort actually means kill this Lisp process. So what we want is we want to return to the top level. So that we can, I guess we see what is wrong. So we leave this error context. We're in the middle of this exception that just happened. So we say 0, then we're back to where we were before we called that function. And given our understanding of the error, what's our problem? I put the wrong predicate here. Not list. Yeah. How does that work? So this is taking advantage of the overloading of nil. So what we're trying to test, want to test, is whether list is the empty list. And the empty list is nil, and nil can be interpreted as false, as a Boolean. So not of false will be true. But that feels a little roundabout to me, to actually sort of take advantage of that overloading and confuse the list, empty list, with the truth value nil sort of deliberately. There is an idiom to test for empty list. Exactly. So that's the idiom. So don't write EQ list nil. Not of list is over queued, I would say. Null of list is the most concise way of testing whether we're looking at the empty list. Okay, let's see whether that helps. I'm still learning my slime commands here. Previous command. Well, there it is. Okay, so let's see. So is this actually correct? Bar is the list containing foo, bar, foo, foo, baz. And now we've swapped foo for baz. And oh, it looks good, doesn't it? Our work is done here. I would like a sort of quality assurance test engineer to protest. Do we have any in the audience? Yes. Go ahead. So the second element is bar, not foo, shouldn't change, but it becomes foo. So how did that happen? So that appears to be in the case where the current element is actually not what we should replace. Which case is that? The one down here. Yes. Whatever the current first element. Yes. So there we were accidentally always making the current element x when it was anything but x. So we were putting foos everywhere where there was something that was not foo before. Okay, evaluate. Let's try that again. You can't see what I type, but I changed the definition and then I evaluate it. Control meta x. And then I go to the Lisp prompt to do my interactive testing. There was a comment in the back. I need another condition, you say, here in the cont before the default. And what's the condition testing? Equal first list. Okay. Oh, sorry, why? Yes. Ah, okay. I see what you're doing, I think. So what effect does that give? So bars on the screen. Now all foos have become baz. And otherwise, we see no difference.
Isn't it correct though? The last line.
It's the same as before. So yes, it looks correct to me, but it depends on how we interpret swap. Let's again look at the goal is to replace every element matching X with Y in the list. So you were interpreted, so it's more replace, you were misled, you were allowing yourself to be misled by swap, and you were wanting to also replace all Y's in the list with X's. But somehow that actually didn't work. So for what we asked you to do, this clause is not desirable. Nevertheless, I'm surprised it doesn't work. Can we explain that? Did I actually evaluate that? No, I didn't. Do I have all my parens there? Now it's evaluated. And now we actually see that the last element, which is bas, has been swapped with foo. So now we have what you thought we asked you to do, but it's actually not what we asked you to do. So let's take that out again. Okay, I thought we would actually generalize this function and make it a higher order function. So I would assume that we have now satisfied what we asked for here in the exam, even though you might quibble with us and say the exam question is not precise enough. Because we say every element matching X, it's a pretty general term, and we give you one example where we use strings. So we don't say whether the function should only operate over lists of strings, and if not, then we don't say exactly what comparison it should use. There's a question here.
Could you use like a loop to just iterate through the list, and if you encounter an element that is equal to X, set it to Y?
A what? Use a what? No, you said loop. We haven't introduced that. But we hope to get to that. So try to avoid using destructive operations. But let's return to that later. We haven't, so currently we only have recursion. So let's make the function a little more generic and actually make it a higher order function where we give it a predicate to actually parameterize how objects are compared. So we need to give it an additional argument, and the fairly strong convention would be to make that a key parameter. And let's say we default that to EQL. That is what the standard library typically does. So now we generalize this function. We make it a higher order function. We give it an additional test predicate, which we default to EQL, and we decide to make these additions optional and named parameters. Okay, so now to actually use that predicate in comparison, what do we have to do? There was one place where we had hardwired a decision about how to compare. That's here. So instead of equal, we want to use whatever predicate we're given. Test. So in scheme, you would write it like this. But scheme is a Lisp 1, and we can't do that. So we need to invoke that function object that is the value of test now. So here we need to be careful and think carefully about the status of that symbol test. It's a named parameter to the function. So test is a symbol. It names a parameter to our swap function. When we call the function, the named parameters become local variables, we said. So they will have value bindings inside of the function. The value of that variable will be a function object. So we need a way of invoking a function object. Yes. Fun call. So we call the function that is the value, we call the function object that is the value of the local variable test. If we did hash quote test here, that would mean that test is the name of a function and we want to obtain its function object. But test is not the name of a function, it's the name of a local variable. So test is a function object. The value of test is a function object. We can evaluate that symbol test, obtain the function object and invoke it with two arguments, namely the current first element and list. And now if we try that, we've broken it. No longer works. So here's the original bar. And what comes back is unchanged, even though there are many foos that we should have replaced. How is that? So our test apparently does not work. It never tests true, even though there are cases where we would like it to test true. That's because we default test to hash. So we're not providing in this call a parameter for the keyword parameter test. That means it will have its default value, which is the function object EQL, which is an identity function that can also deal with numbers and characters. But for strings, we don't want to compare identity. So we actually need to give it a different predicate. And how would we do that? We add an additional argument and we introduce it by its keyword name, and it better be a function symbol, and we want, well, in this case we could actually use string equal, because in this call we're only giving it strings. I see. So abort 0. Thank you. And now the foos have become bases. So we have converted we have generalized our swap. This is beyond what the 2013 exam question asked us to do. And have made it a higher order function that we can now parameterize and give whatever test predicate is suitable for what we're trying to accomplish. Yes? Well, as you say it, there's certainly two foos. Ha 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 ha! Very good, thank you. So even our one, I mean, we have not been very good about testing so far. We've only tested one case, and even that didn't succeed, even though I was prepared to accept it because it had replaced one foo. But the other foos it actually hadn't replaced. Why is that? Because the recursion, of course, needs to pass down whatever test we are actually given. Because otherwise, in the recursive calls, there's no argument for the test parameter, and it will default to EQL again. Oh, that was cute. And that's much better. All right. I could actually continue for the rest of the hour, but I think I have a few more slides I want to go through. And next week, as part of we'll have a quiz next week, and one of the quiz questions I expect will be whether you find the live coding useful. But there won't be points for that question, so whatever answer you deem correct is the answer we want. All right. So think about that, please. That was higher order functions, variable, arity, functions, different ways of identifying function parameters, identity versus equality. Now a very brief detour. We won't in lectures introduce the common Lisp macro facilities, but it's often considered one of the greater features of Lisp. It essentially gives us a programming language where programs can generate programs, self-modifying code. So the code Lisp as expressions can be manipulated by Lisp code before it's actually compiled. And I can use that to extend, among other things, the syntax of the language and to control or prevent evaluation. That is, I can use macros. So what we've called special forms is typically implemented by means of macros, because macros happen before the standard evaluation rules of evaluation apply that we introduced last week. And that means the macro gives us the control mechanism for cases where we actually don't want all of the arguments evaluated. So the Boolean connectives and or the conditional evaluation, if and cont, the sort of special forms for defining things and assignment, all of these can be implemented using macros. But we won't teach you macro writing, but the Seibel book discusses it in some length. But coming up next is actually something that is maybe the poster child application of Lisp's ability to extend the language within the language. So far we've used recursion whenever we needed control over a sequence of things. But there's of course always going to be an alternative, iteration. And recursion is a powerful control structure, an elegant one, but sometimes iteration is just more natural. When I want to go through a list, or when I want to count from 1 to 6, I can do that recursively, but I might as well do that iteratively. And here are some examples of historic or of specialized iteration constructs, special forms in Lisp. Do list, one iteration variable x that will go through the list, and then a body, and that will be executed as many times as there are elements with x bound to that element. Or do times a variable and an upper bound, and that will be executed for x in the range 0 to 5. So 6 times. And what I'm doing here in each of these is I actually give myself a local variable that I initialize to the empty list. Remember, let creates a local variable. It's only visible in the body of the let. Then I use this iteration to go through the numbers 0 to 5. In one case specified as a list of numbers, in the other case enumerated by do times. Test each of them for evenness, and when that succeeds, I push x into the result list. Push, remember, is a macro that does so push xy expands into setfy cons xy. It puts the x, its first argument, into the new first position of y and changes the assignment, the value binding for y. And because I push them, I collect them in reverse order. At the end of the day, what I return, I reverse the list of numbers that I have collected so that they come in the same increasing sequence. It's not the main point here really. Do list and do times are okay for simple iteration. I have stopped using them. Whenever I feel like doing something iteratively, and that actually happens often, then there is one general iteration construct called loop, the mighty loop, and that's very general and versatile. So C introduced the tripartite for iteration control. That was pretty general in its days, certainly. Loop is a lot more general, as you'll see. So loop can do pretty much all sorts of iteration. Let's look at a few examples. And everything that's red here are loop keywords. So they're part of the syntax of the loop macro. And what is not red are either variables. So these symbols, I will be a variable used in each step of the iteration, a local variable, or values. Oh, this 50 of course should not be red. So this just means count, so let I, variable I, iterate in the numeric range from 10 to 50 inclusive, incrementing by 10 each time, and collect these i's. And what I get are the numbers 10, 20, 30 to 50. Some people feel this doesn't look a lot like Lisp because there are actually few parentheses. Rather than parenthesizing richly, as is done in the core of Lisp, the loop macro puts heavy weight on these prepositions, those little control words, if you will. And the idea is that this almost reads like a sentence. Some people even say almost like poetry, loop poetry. So, for I from 10 to 50 by 10 collect I. I mean, that's almost English. So it's essentially a mini language for iteration. Sometimes criticized because it reduces the uniformity, the fully bracketed prefix notation that Lisp is fond of and known for. So Paul Graham, one of the Lisp wizards, is on record saying loop is one of the worst flaws in Common Lisp. I tend to disagree. That's a purist's accusation. Loop is one of the most powerful and transparent iteration constructs across all programming languages that I know. So it really does a very good job. And it does so without excessive use of parentheses. They're just not, they would get in the way in this case. And even though there's this potential criticism of being non-Lispy, whatever that is, we will push it on you. We'll encourage you to use recursion where that's natural and appropriate, and to use loop for iteration where iteration is what you want to do. A few more examples. Count below 10. So here I'm not saying where to start. Most of these prepositions in loop are optional and have default values. In this case, the default value will be 0. So I will range from 0 to 9. So I don't say to 10, then 10 would be inclusive. I say below 10. So I don't have to do the plus or minus 1 that I often have to do in iteration constructs. There's a when, so I can do something conditionally. And earlier, the accumulator, as it's called, what computes the result of the loop was collect. And now I can actually just sum the values of I at each iteration. So this will go through the sequence of numbers 0 to 9, test them for being odd, and sum together, add together those that are odd. 1 plus 3 plus 5 plus 7 plus 9. That comes to 25. I can loop across the elements of a string. And then I can collect each of that element. And what we're seeing here are Lisp characters. So this is now a list. Collect always returns a sequence as a list. Sum always returns a number. And this list contains the individual characters that I found in that string. I can combine all of these. I can give myself a local variable with foo. So that's the same as if I wrapped a let around the loop. With foo equal to something, so in the body of the loop, foo will have the value list of ABCD. And now I have two for loops, I in foo, that's this local variable, and j from 0. Here I'm not saying 2 or below, so I'm not giving an upper bound. I have an until, I give it an additional stopping condition, and then I have a do. Do just means evaluate this, and format will produce printed output. So here the point of the loop is to go through that list, and well, until the counter variable, no, until I becomes the symbol C, and up until that point, at each step, print out the current counter J and the actual corresponding symbol. So essentially that's printing the elements of that list with their position in front of them. So at position 0 there's the symbol A, at position 1 there's the symbol B, and so on. So yes, let me make a few more comments on this one. So how does loop decide how many iterations there should be, especially when I give it more than one for? For I in something, that will run as many times as there are elements in foo. So that essentially iterates through the list that is the value of foo. For I, for x across, that will go through that string. Earlier examples, for I from 10 to 50 by 10, that says explicitly how many iterations there should be. For j from 0, no upper bound, that will not terminate. So if I just write loop for j from 0, collect j, that will compute an infinite list containing the natural numbers including 0. If it only terminated, but it will not get there. So without an upper bound, this is a loop clause that doesn't terminate. This would be one that terminates when we have iterated through foo. But I combine these with an additional termination condition, and in this case that means I'll actually terminate earlier. I'll terminate as soon as I becomes the symbol C. So in this case already at the third element. If there were no C in this list, then this termination condition would never fire. But then we would terminate when we have iterated all through the list. So I can have multiple stopping criteria, and whatever triggers first will terminate the iteration. Yes, you had a question? So no. So in loop I have when, unless, and if and else, but not cont. So cont is a I could of course do cont, but cont is not a loop keyword. Cont is not part of the loop mini language. Yes.
In the last one, is that not a nested for loop? So
Nope.
at the same time?
Yes, so this is not a nested for loop. Then I would have to write loop and inside of that another loop. This is one loop that actually counts two things or iterates two things in parallel. So there will be some number of iteration steps, and in each step the local variable I or counter variable I will take on as its value one element from foo, and the local counter variable j will be a number starting from 0 and increasing. And these will be the values in each iteration step. So it's like using a comma in the C or C++ for statement. I don't do Java a lot, so I'm not sure whether you actually have that same thing in Java. So there is an AND, but it's unnecessary in this case. So 2 fours will just be parallel. There's more loop syntax in this mini language than I don't want to sort of give you an exhaustive. The Graham book has a the Seibel book has a chapter loop for black belts. We have put that on the reading list, and it's the kind of thing you acquire sort of as you need it. Most of what you want to do in terms of iteration you can do in loop, and it will typically involve prepositions. Well, and some verbs, some commands, do or collect or some. These are imperatives. Or some conditionals. All right, I have even more examples, but we're not going through these today. And I have one sort of high-level summary. I think I'll just put out these slides and encourage you to have a look at the Loop for Black Belts book. No, well, you could write a book, of course, but it's only a chapter. And then next week I'll go through one more example and assume that I have done justice to advertising the mighty, very general and flexible loop macro to you. It's going to be your choice of which tools to use, but there's a lot one can do in loop. All right, we're out of time for today. I'll see you next week. That's my lecture in this introductory block. Second half of next week's lecture will be a quiz. There will be bonus points. There's no other way for you to prepare than to catch up on our reading and work on the assignment, and then the quiz will be fun, we hope. See you next week.